We have a uniformly charged sphere with a radius of 40 centimeters. It has a total charge of 80 nanocoulombs spread throughout its volume. If the following sections were removed from the sphere, how much charge would they contain? So we have this big old sphere, and we're wanting to know if I could reach in, grab a little spherical section that had a radius of 10 centimeters, how much of the total 80 nanocoulombs would it have? Or if we could reach in and take out a little cube with sides of 5 centimeters, how much charge would it have? And likewise with the cylinder. If you think along the lines of density, we've mentioned before, for example, if I had a big old swimming pool full of water and I reached in and took a coffee mug full of water out, would the density change? Density of water would stay the same. The ratio of mass per volume is constant. That's going to be similar to what we're dealing with here, only we're talking charge density. So the charge density, since the charge is uniform, the charge density is going to be constant, so the ratio of charge per volume has to stay constant. So the charge density is the ratio of charge per volume. We can find the charge density from the given information. We know there's 80 nanocoulombs of charge. We know it's a sphere. The volume of a sphere is 4/3 pi r cubed. We know the radius is 0.4 meters. Plugging that through, we know the charge density is 298 nanocoulombs per meter cubed. Or 2.98 times 10 to the negative 7 coulombs per meter cubed. Whichever way is fine. This charge density has to stay constant. Whether we're talking about the sphere, the big old sphere as a whole, or if we're talking about just a chunk of the sphere that we pull out. So charge density is going to be 298 nanocoulombs per meter cubed regardless of which section we're taking out. So we're going to use this relationship again to find charge. Remember, density not only is it total charge over total volume, but it would be the charge on that piece, that chunk that we pulled out, over the volume of that chunk. So the charge on those sections is going to be our charge density, which we know, times the volume of those sections. So the charge on this section is going to be our density, 298 nanocoulombs per meter cubed, times the volume of this section. Since it's a sphere, 4/3 pi, the radius is 10 centimeters, so 0.1 meter. That needs to be cubed. So plugging that through, we get 1.25 nanocoulombs. So that little spherical section only has 1.25 of the total 80 nanocoulombs on it. Okay? The cubical section, same process. Charge density times the volume. This is a cube. Volume of a cube is the sides cubed. So 0.05 meters quantity cubed. So we get 0.037 nanocoulombs. A very small portion of the charge. And likewise for the bottom one. So our charge density. Volume of a cylinder is pi r squared, so 0.08 meters squared, times the length, so 0.15 meters. Nanocoulombs is how much charge it would have. Now the reason I asked you this question, if you remember yesterday we were talking about flux. When we talk about flux through a closed surface, which is specifically Gauss's law, the flux is equal to the Q enclosed by the surface over epsilon naught. we need to be able to figure out how much charge is inside a surface we draw if we're inside of a charged object. And the way we're going to find the charge enclosed is looking at these relationships, looking at density.